Another example, we have in a 4-wire 3-phase system, 2 phases have currents of 10 amperes and 6 amperes at lagging power factors of 0.8 and 0.6 respectively. While the third phase is open circuited, calculate the current in the neutral and sketch the vector diagram. So this is our circuit diagram. We have lines A, phase voltages from line to the neutral, we have VA, and this is line A, line B, and line C. Your line C is open circuited. There is a current flowing in the load, which is your IA and IB. And IA has a power factor of 0.8, that is theta equal to 36.87 lagging. For IB, we have 6. So power factor is 0.6 and theta is 53.13. Now, we have to analyze the vector diagram or draw first the vector diagram. For this one, our reference is the phase voltage, which are the VA, VB, and VC. This VA is 120 degrees difference with respect to VB, and also VB to BC and BC to VA. The current for VA is 10 and has an angle of negative 36.87. So, ito yung theta A. And also, your theta B, or this one is your IB. This is your IB. The current in VB, this one, has an angle of 53.13. So, from BB to this one, IA, is 53.13. Now, we will calculate the neutral current flowing here. So, our neutral current is outward from the node, and our currents IA and IB is toward the node. So, this is our node. And we will perform KCL at this node. So, IN will be equal to IA plus IB plus IC. Add them vectorially. So, IC is 0. Now, we will add IA and IB. We have IA equal to 10 angle negative 36.87 with respect to the reference, plus 6 angle of, this is negative 120, plus the quantity of 120 plus 53.13. Or, you can have the positive angle from the reference, this one, to current IB. So, this is 120 plus, this is 53. So, 120 minus 53.13 plus 120. This is equal to 10 angle negative 36.87 plus 6 angle of 186.87. So, pareho lang yung answer. So, dito natin kinuha clockwise direction, kaya negative. So, IN will be equal to 7.02 angle negative 73.08. Next example. Each phase of a star-connected load consists of a non-reactive resistance of 100 ohms in parallel with a capacitance of 31.8 microfarad. Calculate the line current, the power absorbed, the total kVA, and the power factor when connected to a 416 volts, 3-phase 50 Hz supply. So this is our circuit. We have a per phase load of 100 ohm resistance and a capacitance which has a capacitor which has a capacitance of 31.8 microfarad. They are in parallel. And then we have a line-to-line voltage of 416. So this is the neutral. This is our phase A, phase B, and phase C. This is our neutral. Okay, this is neutral. This is EB. The voltage between the line and the neutral is the phase voltage. So, we will solve first XC, capacitive reactance, that is 1 over 2 pi F times C, that is negative J 100.1 ohms. Now we will solve the per phase total impedance, that is XC is in parallel with R. So, equal to 70.746 angle negative 44.971. Getting the per phase value of your voltage, we have V phase equal to E line to line divided by square root of 3, that is 240.178 volts. Solving now the line current, which is equal to phase current in star connected, we have E phase divided by Z phase. That is, so we made our voltage to be the reference. So you will get 3.395 angle 44.971 degrees ampere. Now the power factor is cosine of 44.971. That is 0.707 leading. So, solving now the power, we have a square root of 3 ELIL cosine theta. That is 1,729.47 watts. This is now the total power of the system. And the apparent power of the system is equal to square root of 3 ELIL, that is 2.446 kVA. The next topic that we are going to discuss is the delta or mesh connection. So in this form of interconnection, the dissimilar ends of the three-phase winding are joined together such that the starting end of one phase is joined to the finishing end of the other phase, and so on, as shown in the figure. In other words, the three windings are joined in series to form a closed mesh as shown in figure B. The three leads are taken out from the three junctions as shown as outward. Directions are taken as positive. It might look as if this is a short of connection or short of interconnection, results in short-circuiting the three windings. However, if the system is balanced, then the sum of the three voltages around the closed mesh is 0. Hence, no current of fundamental frequency can flow around the mesh when the terminals are open. It should be clearly understood that at any instant, the EMF in one phase is equal to the opposite to the resultant of those in the other two phases. So this type of interconnection is also referred to as three-phase 3Y system. This is now the circuit diagram of a delta connection. This is our line A, or phase A, phase B, and phase C. The line-to-line voltages are EAB, EBC, and ECA. The line-to-line currents also are IAB, IBC, and ICA. Phase voltages are EA, EB, and EC. Phase currents are IA, IB, and IC. The direction of our IAB, which is the line current, is towards the node, and it is the difference between the IA and IB using KCL equation. As well as in IBC, towards the node, this is our node, so that is the difference between IB and IC. Also in ICA, it is towards the node, the difference between IC and IA. Line voltage and phase voltage of a delta connection is the phase voltage is equal to the line voltage. So EA, EB is equal to EC is equal to EAB, equal to EBC, and equal to ECA. While in current, line currents and phase current, the IL is equal to IAB, is equal to IBC, and equal to ICA. And also phase currents are I phase is equal to IA, equal to IB, and equal to IC. Now the relationship of voltage or phase current and line current is IL is equal to the square root of I phase. So kabaliktaran dun sa Y connection. Yung E line ang may square root of 3. Dito naman is yung current. So we said earlier that the differences between the phase currents is our line currents. So here is the vector diagram. First one is IAB, so that is IA minus IB. So this is our IA, our reference. IB is 120 degrees and also IC is 120 degrees with respect to our reference. IA minus IB is IA is 1 angle 0 minus the negation of IB. So the negation of IB is here. So IA plus or IA minus IB, that is 1 angle negative or 1 angle 120 is equal to square root of 3 angle 30. So here is the resultant IAB. Now this is your 30 degrees. It is between our phase current and line current. Next one is IBC. So we will get the negation of IC nandito. So 1 angle negative 120 minus 1 angle 120, ito, that is square root of 3 angle 90. So ito yung 90 degrees. This one. Now, what will be the relationship of this line current and phase current? Ano yung angle between them? So 120, this is 120 minus 90 is equal to also 30 degrees. The last one is ICA. So IC minus IA, that is 1 angle 120 minus 1 angle 0. That is square root of 3 angle 150. The resultant now is this one, ICA. What will be the angle between them? So this is 150, and from IA to IC is 120. So 150 minus 120 is 30 degrees. Therefore, the angle between the line current and the phase current is 30 degrees. Same in Y connection. The angle between the phase voltage and line voltage is 30 degrees. So same dito, the angle between the line current and the phase current is 30 degrees. And also the power, same in Y connection. The P, Q, and S. So P is equal to square root of 3 ELIL cosine theta. And also, you can solve that one by 3 times E phase I phase cosine theta. Equal to square root of S, which is our apparent, S squared minus Q squared. And Q is our reactive volt ampere. So square root of 3 ELIL sine theta, 3 times E phase I phase sine theta, and square root of S squared minus P squared. Apparent power is square root of 3 ELIL, 3 times E phase times I phase, and square root of P squared plus Q squared. If we are going to convert our loads which are connected, or loads and sources which are connected in Y delta and delta Y. So balance Y delta and delta Y conversion. This is the orientation for the Y connection. And this one is the orientation for the delta connection. We'll convert the impedances in delta to Y. So that is, impedance in delta is equal to 3 times the impedance of Y. Or the impedance of the Y connection or star connection is equal to the impedance of delta divided by 3. Example, we have 3 similar coils, each having a resistance of 20 ohms and an inductance of 0.05 Henry, are connected in, first is star or the Y connection, the second one is in mesh or delta, to a 3-phase 50 Hz supply with 400 volts between lines. Calculate the total power absorbed and the line current in each phase. Draw the vector diagram of current and voltages in each case. So this is our connection. We have a resistance of 20 ohms and an inductance of 0.05 Henry. So we have to solve for XL, that is omega L, equal to 15.708 ohms. So our per phase impedance will be 20 plus J, 15.708 ohms. So eto siya. Per phase natin is 20 and this one is 15.708. So all the 3 wires has a per phase impedance of 20 plus J, 15.708 ohms. And our line-to-line voltage is 400 volts. So in a star connection, the phase voltage is equal to the line voltage divided by square root of 3, that is 230.94 volts. So in star again, phase current is equal to line current, that is equal to E phase divided by Z phase. So I phase is 9.08 angle negative 38.146 ampere. So power will be equal to square root of 3 ELIL cosine theta. So square root of 3 times 400 times 9.08 cosine of 38.146. So power now in Y connection, total power in Y connection is 4,947.34 watts. So if we are going to draw the vector diagram of the star connected system, we must solve the per phase currents, its magnitude and direction. Our reference is x-axis and the phase voltage EA is in phase with our reference. So this is EA, EB, and EC. So saan natin ilalagay yung mga phase currents? So dapat malaman natin yung magnitude and direction ng mga phase currents. To do that, we must solve each component. So for IA, its voltage is of course EA. So 230, this is per phase, 0.94 angle 0 divided by the impedance, which is 20 plus J, 15.708, equal to 9.08 angle negative 38.146 amperes. Next one, phase V. Phase B is 230.94. Ito. Angle that is from reference to this angle, that is negative 120, divided by the impedance, equal to 9.08 angle negative 158.146 ampere. IC 230.94 angle 120, ito siya, divided by the impedance, equal to 9.08 angle 81.854 amperes. So they are the same in magnitude but different in directions because they are balanced system. So ipa-plot na natin yung mga nakuha nating IA, IB, and IC. For IA, that is from reference to IA is negative 38.146. from reference to IB, that is negative 146 angle, and IC is from reference to IC, we have positive 81.854 amperes. So that is for the Y connection or star. Next one is we will go to delta connection. So in delta, our phase voltage is equal to line voltage equal to 400 volts. For phase A, we have EA divided by ZA. So 400 angle 0 divided by the impedance equal to 15.729 angle negative 38.146 amperes. IB is 400 angle. This is EB. EB divided by Z impedance per phase. So 400 angle negative 120 divided by 20 plus J 15.708 equal to 15.729 angle negative 158.146 amperes. For IC, 400 angle 120 divided by 20 plus J 15.708 equal to 15.729 angle 81.854 degrees ampere. For the line-to-line currents, we have IAB equal to IA minus IB. So, substitute lang natin dito yung value ng IA, which is this one, minus parenthesis the value of IB. You will get 27.241 angle negative 8.155 degrees amperes. For IBC, that is IB minus IC, 27.243 angle negative 128.146 degrees amperes, and ICA is 27.246 angle 111.845 degrees amperes. For power, we have square root of 3 ELIL cosine theta. That is 400 times the line current, 27.241 cosine of 0.786, that is 18,871.343 watts. This is the vector diagram of a delta connection system. This is our phase voltages EA, EB, and EC. These are our line currents. So, ipa-plot lang natin yung nakuha natin dito na magnitude and direction. So, for IAB, nandito siya, negative 8.155. Then, IBC, the angle is negative 128 from the reference to IB. And ICA is 111.845 degrees with respect to reference x-axis. For the power factor, we can get that one by R over Z, or simply this one, negative cosine of 38.146 degrees.